Hi, welcome to Sunil Maths tutorial, functional analysis class number 48. In this video, we learn two very important definitions and then we learn a theorem. So let us see the definition first. Operator. Let capital H be a Hilbert space. Let us take capital H be a Hilbert space, and T is a continuous linear transformation. T is a continuous linear transformation from capital H into capital H. Then T is called an operator. Then T is called an operator on a Hilbert space capital H. On a Hilbert space capital H. So you observe that operator definition, one of the important definition. Let capital H be a Hilbert space, and T is a continuous linear transformation from H into H. Here the domain and codomain is same, capital H. Then this T is called an operator on the Hilbert space capital H. Now let us define adjoint of an operator. So let capital T be an operator. Let capital T be an operator. Let capital T be an operator on a Hilbert space capital H. Then there exists an unique operator. Denoted by T star on capital H such that it satisfies the condition inner product of Tx comma y is equals to inner product of x comma T star y. Remember this condition. Inner product of Tx comma y is equals to inner product of x comma T star y. Then this T star is called an adjoint of an operator T. So very important definition. Next theorem completely depends upon this definition. Let us see. Capital T be an operator on a Hilbert space capital H. There exists a unique operator denoted by T star on capital H and defined like this. Inner product of x comma Tx comma y is equals to inner product of x comma T star y. If this T can be shifted to right side, it becomes T star. T star can be shifted to left side, it can becomes T. Then this T star is called adjoint of an operator T. So let us see the next theorem, and very important theorem. This is known as properties of adjoint of an operator also. The adjoint operation capital T maps to T star on B of H. Oh, here you learn this symbol B of H. B of H means script B of H. We read it as script B of H. Script B of H means the set of all operators defined on Hilbert space. What it means? This is the set of all operators defined on Hilbert space capital H. So the adjoint operation T to T star on B of H has the following properties. Let us see one by one. T1 plus T2 whole star is equals to T1 star plus T2 star. Alpha T whole star is equals to alpha bar into T star. T1 T2 whole star is equals to T2 star into T1 star. T double star is equals to T. Norm T star is equals to norm T. Norm T star T is equals to norm T square. These are the 6 properties of this operation norm T to T star. So So okay, we prove one by one. The very first one, the very first one, T1 plus T2 whole star is equals to T1 star plus T2 star. To prove this, let us consider, to prove this, let us consider one inner product. Inner product of x comma T1 plus T2 whole star, T1 plus T2 whole star into y is equals to. This is inner product of x comma T1 plus T2 whole star y is equals to. By definition of adjoint of an operator, this T1 plus T2 whole star can be shifted to first term. Then it can be written as T1 plus T2 into x, comma y. Here it is the operation. We know that already, we learn in the definition. You see here, inner product of Tx comma y is equals to inner product of x comma T star y. Inner product of x comma T star y. That's it. So by using that property, this can be written like this. Inner product of x comma T1 plus T2 whole star y is equals to inner product of T1 plus T2 into x comma y. So that's it. I'm sorry. Yes, this is. Now we split the inner product. This can be written as inner product of T1x plus T2y. I'm sorry. T1x, T2x, comma y, which is equals to inner product of T1x comma y plus inner product of T2x comma y. Again, use the same definition, self-adjoint operator here. Inner product of Tx comma y is equals to inner product of x comma T star y. Applying the same definition here, you can write like this. Inner product of x comma T1 star y plus inner product of x comma T2 star y. Again, by the sum of the inner product of spaces x comma T1 star y plus T2 star y, which can be written as inner product of x comma T1 star plus T2 star into y. So in the left side we have, you observe clearly, in the left side we have inner product of x comma T1 plus T2 whole star y is equals to inner product of x comma T1 star plus T2 star into y. So we prove this inner product. Inner product of x comma T1 plus T2 whole star y is equals to inner product of x comma T1 star plus T2 star into y. So this is nothing but the first element is x, you can remove it. T1 plus T2 whole star y is equals to T1 star plus T2 star into y. Here the vector y is not equals to 0. Obviously you can conclude that T1 plus T2 whole star is equals to T1 star plus T2 star. So that's it, which is required one. T1 plus T2 whole star is equals to T1 star plus T2 star. Next, we prove the second property. That second condition is alpha t whole star is equals to alpha bar into t star. This is the second property of the operation. So let us check it. Again, here also you consider one inner product. Inner product of x comma alpha t whole star into y. So you can shift this to first term. Obviously it becomes alpha t into x comma inner product of y, which is equals to inner product of alpha tx comma y. So it can be written as alpha is a scalar, so write outside the vector alpha inner product of tx comma y. Now shift this t to that side, so you can write alpha x comma t star y. Now move this alpha into inside, so it can be written as x comma alpha bar t star into y. So we prove this condition. Inner product of x comma alpha t whole star into y is equals to inner product of x comma alpha bar t star into y. So again this is equivalent to alpha t whole star into y is equals to alpha bar t star into y, where y is not equals to 0. So you simply conclude that alpha t whole star is equals to alpha bar into t star, which is required second property of our theorem. Alpha t whole star is equals to alpha bar into t star, where this alpha is a scalar, remember that. Now we prove the third property. Let us see the third property, third condition. T1 T2 whole star is equals to T2 star into T1 star. T2 star into T1 star. Again, to prove this, let us consider an inner product. Inner product of x comma T1 T2 whole star of y, which can be simply written as T1 T2 into x comma y. Again it can be written as T1 T2x comma y. Again it can be written as T2x comma, we shifted this T1 to that side, it becomes simply T1 star into y. Now shift the next, in the next step, shift the T2 also to that side, you can get x comma T2 star into T1 star into y. So we prove this inner product of x comma T1 T2 whole star into y is equals to inner product of x comma T2 star into T1 star into y. Again this can be written as T1 T2 whole star into y is equals to T2 star into T1 star into y. Again this y is not equals to 0. You simply conclude that T1 T2 whole star is equals to T2 star into T1 star. So this is the required third property. Now we go for fourth property. T double star is equals to T. That fourth property is T double star is equals to T. So to prove this, again we consider an inner product of x comma T double star y is equals to x comma T star whole star y. So T star whole star can be transformed to this side. So that becomes inner product of T star x comma y. So this can be written as inner product of y comma T star x whole bar. I think everybody knows this property of inner product space. Inner product of x comma y bar is equals to, bar means conjugate. Inner product of x comma y bar is equals to inner product of y comma x. We are applying that. Now again here we convert this, we move this T star to this side. So obviously this becomes ty comma inner product of ty comma x bar. Now remove the conjugate, it can be written as x comma ty after removing this conjugate. So we prove simply inner product of x comma t double star y is equals to inner product of x comma ty, which is trivially implies as t double star is equals to t, which is required fourth property. Now we prove the fifth property. Norm T star is equals to norm T. The fifth property, norm T star is equals to norm T. So right, we prove this. We know that by definition of norm T, we have norm T is equals to supremum of norm T of x such that norm x less than or equals to 1. Now replace in this definition t by t star. Replace t by t star. Obviously you get norm t star is equals to supremum of norm t star x such that norm x less than or equals to 1. So now consider, let it be equation number 1 and then we go for it. Let it be equation number 1. We write the norm T star. Now let us consider norm T star x whole square. norm t star x whole square. Norm t whole square means inner product of, everybody knows that norm x square is equals to inner product of x comma x. In a similar manner, norm t inner product of t star x t star x. Norm t star whole square can be written as inner product of t star x into t star x. So it can be written as, if you shift this t star to this side, it becomes simply t star x comma x comma x. So this is nothing but t star x comma x. So you can norm t star x whole square is equals to, you can write like this, even mod also, mod t star x, inner product of mod t star x comma x. So after using the Schwarzschild inequality, this is less than or equals to norm t star x into norm x. Again this can be replaced by, in the left side we have norm t star x whole square. In the left side we have norm t star x whole square. Again you can split this norm, you simply get norm t star x into norm x. So now you observe on both the sides, norm t star x square, norm t star x, so two terms get cancelled. So remaining terms are norm t star x is less than or equals to norm t into norm x. Let it be equation number 2. Now using this equation 2 in equation 1, here it is equation 1, observe carefully. So using equation 2 in equation 1, obviously we get norm t star is equals to supremum of norm t star x such that norm x less than or equals to 1. So applying equation 2, we get less than or equals to supremum of norm t into norm x such that norm x less than or equals to 1. So this is obviously because norm x is less than or equals to 1. So this is less than or equals to norm t. So what we show that norm t star is less than or equals to norm t. Let it be equation number 3. Now replace capital T by T star in equation 3. If you replace this, so obviously you get norm T double star is less than or equals to norm T star. Norm by property number, previous property, norm T double star is equal to T. So you simply get norm T is less than or equals to norm T star. Equation number 4. Now observe equation 3 and equation 4 carefully. They are converse to each other. From equations 3 and 4, we conclude that norm T star is equals to norm T. Norm T star is equals to norm T, which is the required fifth property of our theorem. This is the fifth property of our theorem. The next one and last property, sixth property, let us prove that. The sixth property is norm T star T is equals to norm T square. Norm T star T is equals to norm T square. So it is a very simple calculation. Let us see. Norm T star T is always less than or equals to norm T star into norm T. Norm T star into norm T. So this is simply property. But actually we show that norm T star is equals to, in the previous condition we show that norm T star is equals to norm T. So which is less than or equals to, here I am replacing norm T into norm T. Norm T into norm T, norm T square. So what we show that, therefore we conclude that norm T star T is less than or equals to norm T square. Let it be equation number 1 for this. Again, by definition we have norm T is equals to supremum of norm Tx such that norm x less than or equals to 1. Squaring on both sides, norm T whole square is equals to supremum of norm tx whole square such that norm x square is less than or equals to 1. Let it be equation number 2. Equation number 2. Now we conclude that norm tx whole square is equals to inner product of tx comma tx, which is equals to inner product of tx comma t double star x, because t double star is equals to t. It can be written as inner product of tx comma t star whole star x. Again it can be written as t star tx comma x, because this can be this operation, this adjoint can be shifted to here, then t double star becomes t star, which is equals to by applying Schwarz's lemma here, norm tx whole square is equivalent to mod inner product of t star tx comma x. Now applying Schwarz's lemma here. What is Schwarz's lemma? Mod inner product of x comma y, is less than or equals to norm x into norm y. By applying this condition here, it is simply less than or equals to norm t star t into norm x into norm x. So norm x is less than or equals to 1. So this implies as norm t star t, which is less than or equals to norm t star t. So I repeat here. Okay, one more step, norm tx square. So in the left side we have norm tx whole square. Let it be equation number 3. Now you have to observe equation 2 and equation 3. That's it. That is the important point here. What is equation 2? Norm t square is equals to supremum of norm tx whole square into where such that norm x square less than or equals to 1. You see this equation number 3, norm tx whole square less than or equals to norm t star t norm x square. So using equation 3 in equation 2, we get norm t square is equals to supremum of norm tx whole square such that norm x square is less than or equals to 1, which is equals to supremum of norm t star t norm x square such that norm x square is less than or equals to 1, which is simply less than or equals to norm t star t. Let it be equation number 4. Now you observe equation number 1. Norm t star t is less than or equals to norm t square. In the left side we have norm t square is less than or equals to norm t star into t. So combining or from equations 1 and 4, we conclude that norm t star t is equals to norm t square. This completes the proof of our last property, 6th property. You can in a similar way, from this 6th property, you can conclude like this. Norm t star t is equals to norm t square. So obviously this is equivalent to the condition norm t star is also equivalent to norm t square. Just I replace their positions. That's it. This completes the proof of our theorem. All these 6 are the properties of adjoint of an operator. Everybody simply remember these properties, but the important thing here you have to remember there are certain conditions. Not conditions, symbol script b of h. This is the set of all operators defined on a Hilbert space capital H. This is the one example and one symbol you have to learn. And T star T star means adjoint of an operator. T star means which is known as adjoint of an operator. T star, remember that word, adjoint of an operator T. And this T star has one simple property, that is inner product of tx comma y is equals to inner product of x comma t star y, inner product of x comma t star y, and this is known as adjoint of an operator, adjoint of an operator. And also operator means that is also a continuous linear transformation defined from a Hilbert space into another Hilbert into itself. It means here the domain and the codomain is same, that's why it is known as operator. And these properties are very simple to remember. These 6 properties are very simple to remember. Keep learning. Wish you all the best.